integrating by parts, if we start off looking at sort of basic integrals, then if I integrate x, I can do that. I get x squared over 2, remembering the rule standard integral, add 1 to the power divided by the new power. So that's okay. I can differentiate x to get 1, so I can integrate or differentiate this without any trouble. I can also integrate sine x to get minus cos x, check on your table. I can differentiate sine x to get cos x. So I can integrate and differentiate these functions separately. The problem starts when I integrate them multiply together, and that's what we've been looking at. I've got one function, x, multiplied by another, the sine x. I can't just integrate them separately in the same way as I couldn't differentiate them separately when we were looking at differentiating functions multiplied together. To differentiate these, I use the product rule, and here it is. A differential is one bit multiplied by the differential of the second plus the second bit multiplied by the differential of the first, that you might remember, differentiating. And if I integrate both sides of this thing, then we end up with this, because the integral of a differential gets rid of that. We end up with just uv, and we end up with this here, which is the formula we use to do integration by parts. So that's the formula that you'll be given in the exam. You're not expected to remember it, but we're now going to practice using it. So if I have to integrate something like x sine x, I use this formula, which is the integration by parts formula. I let one bit equal u, so in this case x, and I let the other bit equal dv, which is sine x in this case. And it's crucial, as we've been discussing, which is which, and we'll see why it's crucial when we go through it. If we now look at our formula for integration by parts, the integral of u dv, so that means if I let that equal u and this equal dv, then the integral of x sine x, which is what we want, equals u, which is x, times v. Well, if dv is sine x, v must be the integral of that. So whatever we call dv, in this case sine x, we must integrate to get v. Minus the integral of v, well that's, we've already integrated, so we know that now, du. Well, du is the differential of whatever we've called u, so du is the differential of x. So the method is, the bit we call u, x in this case, we differentiate to get 1, and the bit we call dv, in this case sine x, we integrate to get minus cos x. So, Warren, the bit we call u we differentiate, the bit that we call dv we integrate. So one part of this we're going to differentiate, one part we're going to integrate. And it works because when we differentiate one bit, x disappears. That's the key. If I differentiate x, x disappears, so then I know I'm going to be left with an integral that I can do. So carrying on with the example, the integral of x sine x dx, our original integral, I'm going to call xu, and dv sine x becomes x, which is u, times v, which is minus cos x, the integral of sine x is minus cos x, minus the integral of v, which is minus cos x, du. And this is the crucial bit, because that's just 1. So tidying up, it becomes minus x cos x, minus minus gives plus cos x dx, integral of cos x dx, which gives us this, minus x cos x plus sine x. And then at the very end, add the c. And so, we end up, finally I will just write this the other way around to put the positive term first, so that's our answer. And if you want a little extension activity that we had to go at a minute ago, you could differentiate this and see that you get back to this, which you should do. And there is the answer if you want to look at it, so you can print it out. So we're now looking at another example. In this example, and this is the way the method works, and it always works this way, that's the beauty of it. I've got to decide to call one bit u, and in this case I'm going to let that be 5x. The bit I call u is, hopefully, when I differentiate it, going to mean that the x disappears, and it does. Look, if I let u equal 5x, the differential is 5. So that means the next bit I've got to call this dv. So dv is cos 2x, so I've got whatever I call dv, I have to integrate, so v is a half sine 2x, as James says. Okay. Now we just got to plug it back into the formula. So the integral of u dv equals uv minus the integral of v du. That's the formula for integration by parts. So that means that the integral of u dv, the integral of u, which is 5x, dv, which is cos 2x, in other words our original integral, equals u, which is 5x, times v, which is a half cos 2x, sorry, sine 2x, minus the integral of v, which is a half sine 2x, du, which is 5. And we end up with that. I can tidy up a bit. 5x times a half, so that's like 5 over 2 x sine x, or sine 2x rather. I can bring the 5 over 2 outside the integral, leaving me the integral of sine 2x inside. And lo and behold, we're left with an integral that we can do, because that's just a standard integral. The other function, the x in this case, the 5x, which was why we couldn't do this first integral, was because there were two functions multiplied together. One of them has now disappeared, so it's just a standard integral. Sine, integral of sine is minus cos over 2, so equals 5 over 2 x sine 2x minus 5 over 2 minus cos 2x over 2 plus c. And then we can try and tidy that up. So there's a good case for tidying this up. We can sort signs out, and we can also factorise to a certain extent. So have a go, see if you can tidy that up algebraically. So factorising, 5 over 2 can come outside the bracket, minus and minus gives plus, so we end up with that.